Alright, so in this 1 hour tutorial, my goal will be to try and illustrate some of the principles that we have been learning through some very simple numerical examples. So we'll solve some problems and try to see how the mathematics that we are doing separately in other lectures applies in real world design problems and so on. So today we will solve some simple problems related to the fundamentals of heat transfer lecture earlier in the day, and then there are 2 more tutorials coming up tomorrow and the day after, in which I will give a demonstration of solving heat transfer problems using finite element simulation tools. And then in the tutorial on Thursday, we'll take up another problem related to lithium ion batteries. So 4 tutorials in all during this class. So we have earlier today looked at thermal conduction and convective heat transfer. So those are the 2 things that I want to illustrate using a simple example in this class. So suppose you have a lithium ion cell that is shaped like a box, and typically there are 2 types of lithium ion cell constructions. One is called a prismatic cell, which is sort of like this, and the other is called a cylindrical cell. So for now, let's just focus on a prismatic cell that sort of looks like this. Typically these prismatic cells are very thin and very broad in the other 2 directions. So suppose this cell has a volume of V, and I will always cross my V because I want to distinguish this from velocity, right? So this is volume, and the regular V will denote velocity, right? We will learn as this class goes forward that this lithium ion cell generates heat. So there is some internal heat generation that happens inside this cell. This has units of watt per meter cube. Okay, so if you multiply these 2, you will get the total wattage of the cell. And my goal is to be able to remove this total wattage from the cell so that it does not start heating up. Okay, the most common way to do that would be to blow air over it. This air comes in at some temperature T infinity and some velocity U infinity. I have a fan and I'm blowing air over this. Okay, and the question is, how much air velocity or speed is needed to remove the heat generated by the cell. Right? Perhaps you work for a automotive company that has these cells that will go into the electric car, right? And the question they are asking you is, what kind of fan do I need in order to be able to remove all the heat that is generated by this cell? Yeah, it's a very practical question. So how do we address this question? Well, Q triple prime multiplied by V is the total heat generated by the cell. Oh, this has units of watts. My airflow should be such that all of this heat is removed. If my airflow is not capable of removing all this heat, then whatever heat remains inside the cell will cause what? It will cause temperature rise, right? It will cause enough temperature rise so that there is equilibrium. And that temperature rise is not desirable. Tomorrow we will learn a bunch of bad things that happen inside a cell if it gets too hot. And that is why my motivation here is that I don't want to um, um, have any heat in there remaining unremoved. We will also learn tomorrow that most cell manufacturers specify a certain upper temperature limit up to which the cell can be considered safe. Typically that number is about 60 degrees Celsius. So this cell is at some temperature T cell which is around 60 degrees C. If it goes beyond 60 degrees Celsius, we are entering dangerous territory where a lot of bad things can happen. What bad things we will learn tomorrow. For now, let's just say that I want to design the system in such a way that the temperature of the cell does not exceed 60 degrees Celsius. Whereas the air that I have at T infinity, what's a reasonable value for T infinity? Sure, let's say 20 degrees Celsius. But here's the problem. If I'm going to design my electric car based on this, and if I take it to Rajasthan or some other place in the middle of summer, right, then any system designed based on these numbers, there is no guarantee that it will work, right? It might completely fail because this 20 degrees C number could very well be 40 degrees C, right? In order to do a conservative design, I must assume worst case scenario, right? And I must actually assume this number to be 40 degrees C. For now, let's stick to 20 degrees C. In fact, I will try to do most of my analysis in symbolic form so that you can go in and plug in any number that you desire. I don't want to do this in terms of actual numbers as much as I possibly can. Okay? Well, so then I think the only remaining factor is, or the only other design parameter that I still need to fix is this U infinity. Okay? The question is, what should be the value of U infinity in order that this temperature remains at 60 degrees Celsius when I am blowing air at 20 degrees Celsius. That's the key question. Okay? To answer that question, we have to appeal to some of the heat transfer theory that we have learned in our previous class. You see, earlier we had learned that if I have a body with a solid body and a fluid passing over it, then the amount of heat transfer that occurs is given by H delta T. Yes? That is the equation that will help us here. In this case, delta T is T cell minus T infinity. Sorry. The question is, what is the value of H? What is Q double prime, by the way? Q double prime was whatever heat that it was generating. This is Q double prime times A. This is the total heat being generated. If I divide that by A, I will get Q double prime. So let's do that. Q double prime therefore will be Q triple prime times the volume divided by the surface area. Yeah, so you can see that the pieces are coming together. I would like Q triple prime times V over A to be greater than H times T cell minus T infinity. No, sorry, the other way around. the amount of heat that I remove must be greater than the amount of heat that is being generated. Correct? And I can write this as H must be greater than Q triple prime V over A times T cell minus T infinity. So that's the first design principle that we have here. We can put some typical numbers and go from there. Typically, the dimensions of a cell, prismatic cell, these are of the order of a few centimeters. Imagine the battery that goes inside a cell phone. Has anybody taken out a battery inside a cell phone and looked at it? What are its typical dimensions? Put a number, 5 centimeters by 5 centimeters. Sure. And how many, what is the thickness? Much less. 0.5 centimeters, fair enough. Right. So let's just put some numbers. This would be 5 millimeters. And these two dimensions will be much larger, say 50 millimeter each. Correct? So that my volume is, I used to be able to do this in my head a long time ago. I can't do it anymore. 1.25 times 10 to the power minus 5 meter cube, right? In fact, if I can open Excel, I would like to do that. So let's see. And if I can show it side by side, that would be even better. Is there not like a local version of Excel? Chrome is there, yeah. So okay, why don't we switch to Google Sheets then? It is. So good, good, wonderful. Thank you. Sorry, what? Okay. And this, which I will also try to. Oh no. Okay, I think that is enough. That is enough. So let's start doing some work here. This is my capital V. Actually, let's. So this is the length. This is the width. This is the thickness. My Q triple prime will go here. And what else do I need? I need the I need the area. I need the volume, and then I need T cell, and I need T infinity. Now let's start putting numbers, right? This is what? This is 50 millimeters, right? So 50.05 meters. This is also 0.05 meters. This is smaller, so 0.005 meters, right? It is very helpful to have everything in meters. SI units, okay? Please stick to SI units. Q triple prime is something that I don't know, and for that actually I will go to a browser and I will download a paper from our lab which has the data, publications, and if I search for actually let's go way down. So in this paper, perhaps we'll discuss this paper in one of the tutorials later. In this paper, we measured the heat generation rate of a lithium ion cell as a function of its discharge rate. As you can guess, the amount of current passing through the cell, it really determines how much heat it generates. The more current that passes through it, the more heat you expect it to generate, because typically heat losses are given by I square R. So as the current goes up, more and more heat will be lost, will be generated. So that is exactly what we had done in this paper, and here is roughly the data. So this cell generates about of the order of 100 watts per liter as a function of the C rate. At small discharge rates, discharge rate I will introduce in the next class, it basically means current, how much current the cell is producing, right? At a low discharge rate, the amount of current produced is less. At a higher discharge rate, it produces more current. And as you can see, the more current it produces, the more heat it is generating. And in fact, it's a square relationship. So let's just pick a number here. Let's say I'm at 4C. At 4C, the amount of heat generated is about 60 watts per liter. So let's start from there, okay? So the amount of heat generated Q triple prime is 60. It was watts per liter. I must convert it to watt per meter cube. So what should I do? Multiply it by 1,000, right? So this becomes 60,000 . This is watt per meter cube. Okay. What is the area? What area should I choose here? Well, it really depends on how I am cooling this cell down. Remember in the previous slide, if I can show the previous slide, we had air blowing over this cell, but we don't really know if the air will blow on this side or on both sides. It is certainly beneficial to design it in such a way that it blows on both sides. Does that make sense? So let's assume that it's going to blow both on the top and the bottom faces, based on which I can say that the area is given by 2 times this times this. okay, and that's meter square. It's extremely important, it takes only 1 second, extremely important to write your units with it. Sometime I'm sure it will save your life, okay. So just carry the units with you, it's very helpful. Of course the volume is easy to do, the volume is given by this times this times this meter cube. Yeah, T cell and T infinity we had already decided. T cell was going to be 60 and T infinity was going to be, did we say 20 degrees C? The advantage of doing this Excel thing is that now I can do my calculations very fast. Having entered all the numbers, the calculations are easy and I can go back and change these numbers as I go through my design process, right? So let's look at the equation we had. QV over A T cell minus T infinity. This is equal to Q times V, times V over A over bracket T cell minus T infinity, right? So this is H, and if you remember from the lecture, the values, the units of H are watt per meter cube, watt per meter square Kelvin. So this very simple calculation tells us that you really need a convective heat transfer coefficient of about 4 watt per meter square per Kelvin. Have we got it all right? I think we have. This looks quite fine. Yes? So the heat generation value, the number that we got here was based on the paper that I showed, right? How do we measure it? Well, I can go to the paper and I can explain how it is measured. Roughly speaking, if I have a body that generates heat, how do you measure how much heat it generated? Huh? Continue monitoring what? Sure. In fact, the whole field of measuring heat generation is called calorimetry. Calorimetry means measurement of calories or joules.
Means heat liberated out of it.
Exactly. So one simple experiment that you can run is take the body of interest, and as it generates heat, immerse that body in a small volume of liquid such as water. This body will generate heat. If you wait long enough, all that heat will go into the water surrounding it, because of which the temperature of the water will rise, right? Then if you can go and measure the temperature of the water before and after your experiment, you can from there say mCp delta T is the amount of heat that must have been generated by this body, right? Provided, there are a number of provideds here, provided there is no energy loss in this experiment, provided you wait long enough, provided that there are no other chemical reactions that are generating heat or absorbing heat, right? So you have to design your experiment very carefully. But once you have done that, you can easily measure the amount of heat that you generate. In some cases, you don't have to do it yourself. There are calorimeters that you can purchase for doing this measurement sort of by pushing a button, right? But if you have a specialized system like a lithium ion cell, then it's possible that you may have to design your own system. So in that paper that I was referring to, we actually designed the whole thing all by ourselves in order to do this calorimetry, to measure how many joules of heat is being liberated. And by doing that, we were able to measure the heat generation rate of the cell as a function of the discharge rate. Perhaps in the fourth tutorial, I will go back to that paper and we can look at that experiment in a lot more detail. One thing that I really want to teach during this entire week also is experimental measurements. How do you measure things? You know, it's very easy to measure something if you really only want to measure it, right? I take a thermocouple, I attach it there, I measure it, and done. But how do you measure reliably? How do you measure in a way that you have full confidence in the measurement is something that takes a lot of time and effort. So I will focus on experimental measurements in the coming lectures as well. Yes.
You can use the environmental chamber.
Yes, something like that. We sort of built a mini environment chamber around the cell by insulating the heck out of it. Okay. What is the meaning of this number? This number is the convective heat transfer coefficient caused by the air blowing over the lithium ion cell, both the surfaces, right? It turns out that this is actually a very small number. 3.75 watt per meter square Kelvin is very small. Even natural convection, which means if you leave the if you leave the cell in still air and don't actually blow air over it, even then there would be some heat transfer because of buoyancy. And typically the convective heat transfer coefficient even for natural convection is of the order of 10 to 100 watt per meter square Kelvin. What that means is that I am most likely going to be able to manage this cell without the need for any external cooling. Even if I just leave it there, it will cool down naturally by itself sufficiently to be able to remove the kind of heat that I have. Okay? Now the battery engineer comes and says, you know what? This is a very small cell. This is typically the cell that goes inside a cell phone, right? And that is the reason why cell phone, the battery inside the cell phone doesn't have a fan blowing air over it, right? Somebody maybe 20 years ago did very similar calculations for a cell phone and showed that look, the battery of a cell phone really does not need any cooling. If you just leave it there, it will cool down enough by itself. However, now when you come to electric cars, the story is very different. First of all, the batteries inside an electric car are much larger. So this number, these two numbers will go up, all these three numbers will go up, right? The discharge rate is quite high. This number that we got was at, if I go back to that, did I close that PDF? Never mind, in that case that's okay. It's a square relationship, which means that this was at about 4C. If the current goes up, this number will also go up, and I have to be careful about that. And then, you know, I have to design it in such a way that this number can be increased for conservative design. Okay? Has anybody left their cell phone inside a car on a hot summer day and come back a few hours later? The temperature inside the car gets very hot. Eventually the battery will shut down. The cell phone will completely shut down, because the cell phone gets so hot that it says, you know what, in order to save myself, I'm just going to switch everything off, right? You cannot do that to an electric car. If you're running an electric car, no matter how hot it gets outside, you can't shut it down. You can't say it's getting too hot for me, I'm going to switch off, right? So while a cell phone can be designed based on some very conservative numbers, the battery of an electric car has to be designed in much more challenging parameter space. This 20 degrees C number needs to be much larger. So we can look at how this design will change for an electric car and see see the two of them side by side. So let's say this is for a cell phone, and I wish I had a mouse. Well, I wanted to select, okay, let's do it manually, paste. In the next tutorial, maybe I'll just use my own laptop, which will make these things a little faster. That's also a possibility, sure. So this is for an EV. So as we have discussed, a number of things will change. This 20 degrees C needs to become, how hot does it get? 35 is nothing, man. 35 is nothing. So, okay, 45 is a decent, more decent number. Yeah. You see, any design needs to have some factor of safety as well, just in case. 45 is, yeah, I think 45 is a reasonable number. So you can see that this number is already beginning to go up. Yeah. If I make my battery larger, instead of 5 centimeters, say it is 20 centimeters, which is not unreasonable. So this becomes 0.2, and this also becomes 0.2, and the thickness goes up. Instead of 5 millimeters, I am maybe 10 millimeters, 1 centimeter. So 10 millimeters is 0.01, correct? I'm just double checking everything. Oh, sorry. Just enter, yeah. So you can see that this number has already jumped by quite a bit, about 7 times, right? Moreover, if this goes up, the amount of current requirement for a cell phone is very small compared to the current requirement for an electric car. So if, let's say, the current output required out of this cell is 10 times that for a 10 times in an electric car compared to a cell phone, then this must go up by 100 times, because the heat generation is I square R, right? So let me just take this and add a couple more zeros here. And now the problem is out of my hand, right? This says that the thermal management of the batteries in an electric car will not be as straightforward as a cell phone. For a cell phone, just leave it and it will cool down by itself. Here I have to do a lot more work. Yeah? I can do a lot of interesting things based on this now. Let me maximize this. Suppose the battery engineer comes to you and says, you know what, you are asking me to provide this kind of a convective heat transfer coefficient. I just don't have the capability to do that. Let's say that they come back and say, oh, you know what, my H value is only 1000 watt per meter square Kelvin. What kind of temperature can you keep the cell at? So you can go back here and you can start changing this number so that you achieve the desired number here. In other words, what should be the value of this in order to get to 1000 watt per meter square Kelvin? One simple way of doing that in Excel is to use this thing called what if analysis, goal seek. And you're saying that I want this number to become 1000, and I'm giving you the liberty of changing this number. Okay, it's gonna do the number crunching and it says 75 degrees Celsius. So what this means is that if the convective heat transfer coefficient that you can provide is only 1000 watt per meter square Kelvin, then your cell will be at 75 degrees C, not at 60 degrees C. Are you willing to live with that? That's the question that your company will then have to answer. You can also go back to them and recommend them to make your cells smaller, either less in thickness or less in size, right? But those are all the kinds of design questions that you can possibly answer from an analysis like this. Okay, any questions? And how are we doing on time? Okay, any questions? By the way, these slides and these materials will be made available. We'll convert everything to a PDF and provide an access to all the students for this material. Let's go back here and I want to make a few more comments. The story in a cylindrical cell is even more interesting, because in a cylindrical cell what happens is that if I blow air over this cell, then this cell is going to get cooled very nicely on the outer surface, but deep inside the cell will have very poor cooling, right? And we will learn in tomorrow's very first lecture that thermal imbalance within the cell is a big problem. Not only do you want to cool down the cell, but you also want to cool it down as uniformly as possible. If one part of the cell is very cool and the other part of the cell is very hot, then that is not desirable as well. Okay? The temperature gradient inside the cell should be minimized as much as possible. And that is one problem that happens in a cylindrical lithium ion cell. Here, the outer surface will cool very nicely. The inner surface, the inner point in the cell will not cool down very nicely. Let's analyze this problem real quick in order to understand what is going on here. Okay? So suppose the radius of the cell is capital R. I'm going to work in the radial coordinate system here. Let's assume that the cell is infinitely long, so that it's a one-dimensional problem. The cell is also axis symmetric from 0 to 360 degrees, right? So under a bunch of those assumptions, I'm jumping forward a little. We'll cover this in the lectures tomorrow, but the governing equation is given by this, plus q triple prime by k equals 0. This is the differential equation that governs temperature as a function of R. No, small r is the coordinate system. Instead of x, y and z, I'm using R. It's a one-dimensional analysis. It's the position, it's the coordinate system. Yes? And capital R is the radius, the actual radius of the cell.
If you are considering this a cylinder,
yes.
Then it has got some sort of thickness,
height.
YR square plus h. That formula can also be applicable.
Yes, but I am neglecting the height of the cylinder.
So we are considering that airflow has been allowing only on the top of the.
No. This is not the top view. This is a cross-section view.
Agreed. So it has been cross-section and we are facing away from the.
Correct. Yes. So here is my cell, and the view that I am presenting is this cut. Agreed?
Transverse cut.
Transverse cut. Exactly. And the air is blowing all over across the cell. Got it? Sorry, I didn't make that clear, but this is a cross-section view, not the top view. Well, the top view will also look the same, I guess. So you can think of it as
Axial.
it's an axial, yes, yeah. Okay, so this is the equation that we want to solve. We will go into the details of where this equation comes from, etc. But in the remaining time I have, I want to solve this equation and show some very important key features from the heat transfer point of view for this problem, right? Let's solve this equation. This equation is not that difficult to solve. Del by del r of r del t del r equals negative q triple prime r over k, right? So if I integrate it once, I get r del t del r equals negative q triple prime r squared by 2k plus c1, yeah? And if I integrate it once more, I can take the r to the other side and integrate it once more to get t equals negative q triple prime r squared by 4k plus c1 log r plus c2. Yeah, everyone with me? Cool. We need to determine the coefficients c1 and c2. What can you say about c1 and c2? It will come from the boundary conditions. Sorry? So I need to write some kind of boundary conditions at r equals 0 and at r equals r. At r equals r, the simplest boundary condition to write is that the temperature of the cell will be exactly equal to T infinity. Right? The air that is blowing over it, if it is gonna cool down the cell perfectly, then the outer surface of the cell will become T infinity. Right? At r equals 0, gradient should be what? The gradient should be 0, yes. Or I can make a mathematical argument that look, log of 0 is not defined, right? Therefore, in order to have a realistic temperature at r equals 0, I must choose C1 to be 0. So C1 must be ruled out in order to ensure a finite reasonable temperature at the center of the cell, right? And from the other boundary condition, I will get C2 is equal to T infinity plus Q triple prime R squared over 4K, which means that T as a function of R is given by Q triple prime over 4K R square minus R square. Correct? And therefore, T max is equal to Q triple prime R squared by 4K. This is the maximum temperature in the cell. Yeah? And sorry, I forgot to add T infinity here. There should be T infinity plus. And there should be a plus T infinity here as well. Right? So what this equation tells me is that the maximum temperature of the cell that occurs at the center of the cell depends on T infinity. Of course, the hotter the cooling air is, the higher will the temperature of the cell be. One very simple way to solve all of these problems is to provide cold air. If I can somehow provide air at 0 degrees Celsius, then the cell will never get hot, right? But where do I get air at 0 degrees Celsius? I can't, in my electric car, also have a cooling system that cools down the air that comes in, right? A refrigerator or something like that. That's too much to ask. And the temperature rise also depends on Q triple prime, the radius of the cell, and the thermal conductivity of the cell. This tells me that the higher the thermal conductivity, the lower will be the temperature of the cell. So if I have two candidate cells from two different companies that I have measured their thermal conductivities to be two different values, I really would like to go with the one that has the higher thermal conductivity. R square represents the geometry of this cell, and the square is a very strong dependence. Right? What that means is that if I double my radius, my temperature rise will go up by 4 times. So I have to be very careful in the size of these cells. I don't want a really large cell. As much as possible, I want small cells. I could have a larger number of cells, right?
Surface area is
Yes, exactly. The surface area is what is creating this trade-off here. Instead of having one very big cell, I really want to have a large number of individually small cells. That is the reason why typically electric cars and most other applications for batteries still use relatively small sized cells. In a typical electric car, the Tesla, for example, the cell that is used has a diameter of 26 millimeters, 260, 26 650 is what I'm thinking of. So 65 millimeters is the height and 26 millimeters is the diameter of the cell, and this cell is called 26 650. That is the typical nomenclature used. Other typical types of cells are 18 650, 21 700 as you said, and so on. Right? The way to read this is that the first two letters refer to the diameter in millimeters, and the last three sort of refer to the height of the cell, 65 millimeters. A typical electric car like the Tesla has about 10,000 such cells. The zero, yeah, I don't know where the zero comes from. It's just nomenclature. So you can think of it as 65.0 millimeters.
Some of the cells earlier
Must have been,
a kind of tolerance structure they could have been.
yeah, possibly.
Even resistance we used to mark there. Some
Hmm.
tolerance, kind of the zero can be.
Yeah. So one reason for an electric car to have a large number of small sized cells is exactly this analysis that we were doing in our Excel sheet. Have I lost my Excel sheet?
the select from there from the
Task bar.
yeah, some Chrome,
Ah, got it. Thank you, thank you, thank you. Yeah, so this is the reason why I want to have small size cells. And sorry, I was also doing some work here related to cylindrical cells. And that yeah, this is where it comes from. The radius must be as small as possible. If I increase the radius, the temperature will go up non-linearly. And of course, if I increase the heat generation rate, then that will also go up. Any questions on this so far? Yes.
still cylindrical cells are so much in fashion. All
Yes.
these are used. And as you mentioned that there is a constraint regarding the heat transfer in the cylinder.
Yes.
Why companies are not doing for prismatic cells?
Well, that's not true. A lot of electric companies are using prismatic cells. I don't know about electric scooters, but in electric cars, the only major company that still uses cylindrical cells is Tesla. Otherwise, Nissan, BYD, etc., they all use prismatic cells. And one of the reasons for that is the surface area, among other reasons.
So surface area means the heat dissipation from the LED over the surface. Can
Yes, exactly. Yes.
take it like or it has been proven?
That
When compared with the geometry of the cells, it's a prismatic as well as circular.
Yes.
Circular, we understood that if the radius has been doubled, then it have been squared for the 4.
yes,
If it's for a prismatic,
we would have a similar relationship.
similar, that's
Sim-
what I'm asking.
yes, exactly. Yes,
So
we would
the
have a
loss to be minimized.
correct. Yes.
Then why Tesla is preferring
They have their own reasons. So, this analysis is fairly simple. What Tesla does is something more complicated. They actually have channels around the cell
for a coolant
for
kind of
liquid
thing.
cooling,
Yes.
right? And the analysis of liquid cooling is
Heat
a little
exchangers
more
they will be
complicated.
casting. They
Yes.
might be using heat exchangers.
Yes. So that analysis is slightly more complicated than what we have done here.
It's a generalized one. So prismatic will be having lesser amount of heat dissipation compared
Correct.
to the cylindrical.
Yes. Yeah.
Since
But
Tesla is using a lot, they might use number of heat exchangers.
they probably need to do that. And of course, heat transfer is not the only consideration. There are several other things.
Yes.
Manufacturing of it is also
Manufacturing is another constraint.
Casing.
We are seeing the lithium and battery cell. It is not like a solid.
Mhm.
It's a film which is going to be rolled out.
Correct. Yes,
Rolling
exactly.
it in a cylindrical phase is a much
So
easier.
tomorrow we will look at the construction of a lithium-ion cell, the jelly roll and all that stuff, where some of these things will become somewhat more clear. Um, um, by the way, if I have a cylinder, do you have a question? Yes, go ahead. Well, typically these cells are very long compared to their diameter, and therefore we can assume them to be infinitely long. You see, the infinitely long assumption is typically valid when the aspect ratio is much larger than 1. In this case, the aspect ratio is 65 millimeters divided by 26 millimeters, which is about 3 or something like that, right? It is not a bad idea to consider the cell to be infinitely long. By the way, I said that the biggest problem happens at the center of the cell, and one very straightforward way of solving that problem is to build a cell with a hole and blow some air through the hole. That way, you will be cooling.
Convolutional heat exchange mechanism. There will be a hole in center. Cells can be located across its radius.
No, I'm talking about a single cell. This is just one cell,
One cell
and I have a hole through the cell.
where heat exchange can happen through the hole.
I can blow some air. I can blow some air exactly through this channel down the cell, and I can remove heat from the very core of the cell.
Internal surface also it can.
Yes, it's a very simple idea, and in fact, we've done some work in our lab that shows that providing such a channel in the middle of the cell actually solves a lot of heat transfer problems, because not only are you now cooling from the outside, but you're also cooling from the inside of the cell. And even if this is a very small channel, and even if you don't blow a lot of air, even then it provides us very good heat removal capability. The simple reason why this does not happen in reality is that it makes the problem, the manufacturing, much more complicated. It is much easier to manufacture a solid cylindrical cell than it is to provide a hole passing through the cell. It messes up a lot of things. For example, if I look at it from the side view, the top and the bottom of the cell are typically used for making the connections, positive and negative connections. If I have a hole through the cell, then I would have to redesign the connections, where to take the metal leads, how to connect them, and so on and so forth. And people have invested many years and millions of dollars for the manufacturing lines that produce these cells. Despite the clear thermal benefit of this, I cannot possibly go to them and say, just because this has much better thermal benefits, that you change your entire manufacturing workflow to accommodate what I am thinking, right? So despite everything that we will learn in this class, I want you all to be cognizant of how real life works. In real life, despite all these improvements and designs and all that, sometimes it's just not practical, economically practical, to actually make it happen that way. Okay, any questions?
For the same capacity of cell, we provide the channel like that, then the size of cell also will increase.
Absolutely. You see, this hole is displacing material that could have stored energy. So the energy storage density of the cell will go down. I am sacrificing material inside the cell that could have stored more charge. I am sacrificing it for the capability of removing heat.
Efficiency could have been reduced if we are introducing that particular hole.
Absolutely, yes. And then it's up to you to decide whether you're willing to pay that price or not. Right? That all boils down to economics and so on. Okay? Any other questions or comments? If not, I think we are past our time. It's a good point to stop here and call it a day. Thank you so much. And we will resume tomorrow morning. Look forward to seeing you all here. We have a lot of interesting topics to cover tomorrow. So get some good rest and I'll see you all refreshed tomorrow morning. Thank you very much.